Context is the information a model can use when it makes a prediction or generates an answer. In this topic, we'll look at features, prompts, chat history, token limits, and external knowledge, and see why context has such a strong effect on model behavior. We've already contrasted traditional machine learning with modern LLMs. Now we can ask the next question. What information shapes their outputs? Context is the bridge between fixed features, prompts, conversation history, and external knowledge. Context means everything the model can use at the moment it responds. In classical machine learning, that might be structured features, rows, columns, labels, or measurements. In LLM systems, context is often text, the prompt, system instructions, chat history, retrieved documents, or examples. The key idea is simple. A model cannot rely on information it does not receive. Context sets the boundary for what it can know, infer, and produce. In classical machine learning, context is usually compressed into features. A person's age, a transaction amount, location, and time become a feature vector the model can process. That structure is powerful, but it is also limiting. The model learns only from the variables we choose to include. If an important signal is missing, messy, or poorly engineered, the prediction may be weak, even when the algorithm is sophisticated. For classical machine learning, context is often fixed. Specific columns, specific values, and specific meanings. With LLMs, context is more flexible. A prompt can combine the task, relevant background, examples of good answers, formatting rules, and earlier conversation. That richness is useful, but it also means wording matters. Change the instructions or examples, and the same model may produce a very different response. Prompt design becomes part of engineering. This difference changes how systems are built. Classical models see the world through a schema defined before training. LLM systems assemble context at request time, using prompts, documents, instructions, and user intent. That makes them easier to update and adapt, but harder to control, test, and keep consistent across situations. An LLM request is rarely just one sentence from the user. It is assembled from layers of context. The system message sets the model's role, rules, and boundaries. The user prompt provides the immediate task. Chat history keeps the conversation coherent. Examples show the desired pattern. Retrieved documents add outside knowledge. All of these are packaged together before inference, so the answer depends heavily on what was included. Think of a system message as the operating agreement for the assistant. Before any user request arrives, it sets the role, tone, safety limits, and expected output format. This gives the model a stable frame for each interaction. But a system message does not teach new facts. It guides behavior. Good system instructions say what the assistant should do, how it should do it, and where it must stop. User prompts are the model's immediate assignment. A vague request, like "tell me something about it," leaves too many blanks. Audience, purpose, length, and focus. A stronger prompt narrows the job. Summarize the sales report in 5 bullets for executives, emphasizing risks. That added context reduces guessing and gives the model a clear target for tone, content, and format. For beginner applications, prompt quality often determines output quality. Conversation history is what makes chat feel continuous. When a user says, "make it shorter," the model can understand that they mean the previous answer, because earlier turns are included in the current context. The trade-off is space. Every old message uses part of the context window, and too much history can add noise or contradictions. Real applications often summarize, trim, or selectively include prior turns, so the model keeps what matters. Few-shot prompting is like giving a student a few sample answers before a quiz. The model does not relearn permanently. It uses the examples in the prompt to infer the pattern you want: format, tone, category, or transformation. This can make outputs more consistent, but each example uses context space, so choose the clearest and most representative ones. Sometimes the model needs knowledge that is private, recent, or changing, such as policies, catalogs, tickets, legal rules, or database records. In those cases, the system retrieves the relevant pieces first, then injects them into the prompt as runtime context. This is the basic pattern behind RAG. Good context makes answers fresher, more specific, and easier to verify. Before an LLM can reason over text, the text is converted into tokens. A token might be a word fragment, a space-related fragment, or punctuation. A simple sentence can become more pieces than you expect, especially with uncommon terms. Everything sent to or produced by the model uses tokens, prompts, chat history, retrieved context, and responses. That is why token count directly affects cost, speed, and how much context fits. Think of the context window as the model's working memory. Every instruction, prior message, retrieved document, example, and expected answer consumes part of that limited token budget. When the window is overfilled, content may be truncated, or the model may struggle to focus. Bigger prompts also cost more and respond more slowly. The goal is not maximum context. The goal is the right context, using summarization, retrieval, or fine-tuning to keep the signal high. The core idea is simple. Context is whatever the model uses to decide its output. In classical ML, that usually means structured features. In LLMs, it includes prompts, instructions, history, examples, and retrieved knowledge, all constrained by token limits. Next, we'll see why context quality matters.